Good morning, guys. Today we're going to work with finding the determinant of a matrix. Now, as you can see, a determinant is a specific number. It's not a matrix. It's a single value that we get by combining all the entries of a matrix in a specific order. So it's just a number that we get. Has lots of uses. We use it when we're solving linear systems or looking at the solutions of a linear system. Use it in geometric transformations. It has some calculus techniques that it can be used for. So a lot of different uses for the determinant of a matrix. We're going to today just work on how to actually calculate that determinant. One thing to note, only square matrices have a determinant. So we can only do determinant of a square matrix. That kind of gets us into inverse matrices, which we'll look at in the next lecture. So starting out, we'll look at a 2 by 2 matrix. And to find the determinant of a 2 by 2 matrix, let's say we have matrix A, and it has the entries A, B, C, D. 2 by 2, remember, 2 rows, 2 columns. That's what makes it a square matrix. Same number of rows, same number of columns. Next, some notation. Determinant of the matrix A can be written DET of A. We can do these vertical bars on A. That's another sign of determinant. And we could just put vertical bars on the matrix. So we're placing the brackets on the matrix with vertical bars on the matrix. All of those are different ways to write the determinant of this specific matrix. The way we actually calculate the determinant is to take the product of the diagonals, A times D, and the product of the other diagonal, B times C, and subtract them in that order. You're always going to start with your top left diagonal and top left diagonal product minus the right side diagonal product. And that's your determinant of a 2 by 2 matrix. Let's look at a couple of examples. Now here you can see we've got 2 examples. We want to find the determinant of each of these 2 by 2 matrices. So we have our matrix A here. We want to find the determinant of matrix A. So if I want the determinant of matrix A, as you can see in our setup over there, we're going to multiply the diagonals, so 2 times 4, minus the product of the other diagonal, negative 3 times 1. So negative 3 times 1. 2 times 4 is 8. Negative 3 and 1 is negative 3. So 8 minus a negative 3 is plus 3. So the determinant of matrix A is 11. Well, if we went through and did matrix B over here, it's going to be the same process. If I want the determinant of matrix B, multiply the diagonals, negative 1 times 4 minus the other diagonal, 2 times 2. And I get negative 1 and 4 is negative 4, negative 2 and 2 is negative 4, so the determinant is going to be 8. That's all it is. There's not much more to it than that. Multiplying diagonals and then combining all of those products by subtracting those products. 3 by 3 obviously has more numbers, so there's a lot more involved as far as the calculations, but it's the same general idea of multiplying diagonally and then subtracting each of those products. So we'll look at the determinant of a 3 by 3 matrix here in just a second. Okay guys, now we're going to look at determinant of a 3 by 3 matrix. There are actually 2 techniques to finding the determinant of a 3 by 3. First one I'm going to show you is the diagonal method. The next one is actually where this diagonal method comes from, but we'll kind of look at this one first because I want to talk a little more about that next one. Diagonal method works a lot like what we did with the 2 by 2 matrices, where we multiply one diagonal and subtract the other diagonal. Only problem is if I multiply one diagonal and subtract the other diagonal, I'm using the same number. That middle number ends up being the same, and we end up leaving out a lot. So there's a lot more to it because we want to pull in all the values of the determinant and the specific location that they're in. So the first thing we do for diagonal method is to copy these first two columns onto the outside of our matrix. So that's step one. Rewrite your first two columns on the outside. Now we're going to multiply diagonally. But now we have three diagonals in each direction. So my first one, AEI, plus the next one, BFG, plus the next one, CDH. That gives all of our left-handed diagonals. Started on the left, worked our way down. Then we're going to subtract all of our right-handed diagonals. So we have BDI, AFH, and CEG. So we take all of our left-handed diagonals minus all of our right-handed diagonals. And you can just add these up, add those up, subtract the two. Some people like to just subtract each of these individually instead of coming up with a sum and subtracting. That's your personal preference, how you want to work those diagonals out. So let's look at a couple of examples where we find the diagonal of each of these. So again, step one, rewrite our first two columns on the outside or on the right side of our matrix. So I'm going to find that determinant by multiplying diagonally. 0, negative 1, 1. 2, 2, 4. 1, 3, negative 4. And that's going to give me my left-hand side. Next we're going to do 2, 3, 1. We're going to subtract those. 0, 2, negative 4. Subtract that one. And set 1, negative 1, and 4. Subtract that one. So we'll add up all the left hands, subtract all the right hands. When you do that arithmetic, you're going to get 0, 16, negative 12, negative 6, 0, and 4. That total sum should be, when we get here, 20 minus 18, which is 2. So the determinant of this matrix right here, as we can see, is 2. So it's very simple as far as it's just multiplying and adding or subtracting those products. It's just, again, it's like a lot of the matrix stuff, just be organized about it and make sure you're very careful and you get the right numbers paired up in the right orders. All right, I want you to pause this video for a couple minutes. I want you to attempt to find the determinant of number 2 right here, and I will wait for a moment for you. Okay, hopefully you're finished, but let's go through and check your work. Step 1, rewrite the first two columns on the right side. And we multiply the diagonals. So negative 1, 2, 2. 1, 3, 3. 2, 0, 4. And then now we'll subtract all of our right-hand diagonals. 1, 0, 2. Negative 1, 3, 4. We'll want to subtract that. A subtraction symbol out there. And then minus 2, 2, 3. Find each of your products. Negative 4, 9, 0, 0. Negative, negative makes positive 12. And that should be negative 12. So we go through. 12's cancel. 9 minus 4 is 5. So the determinant of this matrix right here is 5. That's the diagonal method. Give me a second and I'll get the expansion by minors method up there for you. So let's look at expansion by minors, our second technique for finding the determinant of a 3 by 3 matrix. Now, the way expansion by minors works is we pick one row to work off of. Typically, I'll look for a row that has a 0 off of it, and we can use any one of them. And if none of them have a 0, then you pick one that has the smallest numbers in it, because those numbers we're going to be multiplying by. So if you've got a 0 in there, you can eliminate a whole section because you're going to multiply everything by a 0. So that's where expansion by minors is a little bit nicer than the diagonal method, because you can start canceling out chunks of operations, so you can speed it up. Expansion by minors is also a very, very good technique to go ahead and learn now, because it's actually how we do find the cross product of vectors, something that you'll learn later on in calculus. So very good technique to learn now. Maybe later on in the year we'll get to do some vector work and we can play with them a little bit as far as cross product, but this technique will show up again, so it's very important that you understand how to do expansion by minors. One thing that we need to pay close attention to when we're doing expansion by minors is the distribution of these signs. Where in diagonal method it was add all of our left-handed diagonals and subtract all of our right-handed diagonals. In this, we've got to pay close attention to the signs, where we start with a plus sign and then we just alternate all the way through. And that's going to tell us which ones do we add, which ones do we subtract. So you always start with a plus sign, so plus, minus, plus, minus, plus, minus, plus, minus, plus, and so on. This is actually what we did when we did the diagonal method for a 2x2 matrix, and we'll look at how the expansion by minors is the diagonal method for a 2x2 when we get into class. And you can use this for any square matrix. The expansion by minors works for all of them. So while diagonal method is specific only to a 3x3 matrix, expansion by minors is the technique we use for all square matrices when we're finding their determinant. So it's very important that you learn this and get comfortable using it. So if we look right here, I did my expansion by minors with my first row. So I worked off of row A, B, C. So there's my A, there's my B, there's my C. You can see my signs, plus, minus, plus. Positive, negative, positive. Now that doesn't mean this middle number is negative, it means opposite of whatever B happens to be. If I'd have done my expansion with this second row, I'd have started with the opposite of D, E as it was, so plus E, and then the opposite of F. That's what the plus minus means. It means that we're taking the opposite of some terms, or some entries, and we're leaving some entries as they are. And the way we get these little mini determinants next to it is if I'm working off of entry A, I eliminate entry A's row and column. So when I eliminate its row and column, you're left with EFHI. So we're going to find this mini determinant EFHI. EI minus FH. Now to go to B, I eliminate its row and column, and you can see we're left with D, G, F, and I. D, G, F, I. D, G, F, I. And then the C is going to work the same way. Eliminate row and column for C, and you can see the D, E, G, H. D, E, G, H. So you pick a row to work off of, and then to get the little mini determinants for each one of those values from that row, we just eliminate the row and column for that value, and what remains is going to be our determinant. Or we're going to find the determinant of. Now, if we were to go through and do these little determinants, EI times FH, or EI minus FH rather, all that's getting multiplied by A. Negative B times DI and FG plus C times DH and minus EG. So you have AEI minus AFH minus BDI plus BFG plus CDH minus CEG. So when you've multiplied all that stuff out, what did we get? AEI plus BFG plus CDH minus AFH minus BDI minus CEG. This was our diagonal method. So the diagonal method is just the final setup that we get from expansion by minors. So that's where that comes from. The expansion by minors is much more valuable because it works for everything and not just a 3x3 matrix, which the diagonal method does. So expansion by minors is very, very important that you know it and be comfortable working with it. Let's work a couple of examples, and let's find the determinant of this matrix right now doing expansion by minors. So first we need to pick a row to work off of. I see this row has a 0 in it. That's the one I'm going to grab. That 0 right there I know is going to eliminate this whole chunk because it's first number, it's that first value times this little matrix. So I'm only having to do 2 little products, saving all my calculations. So I'm going to work off this first row, this minor right here. So if I take 0, and remember, plus minus plus times something, minus 2 times something, plus 1 times something. So this is the row I'm going to work off of. So I'm finished with that row. Because I know I'm going to have to eliminate that row every single time to get these many determinants. So I'm finished with it. That's the minor by which I'm expanding. So now we want to figure out what the little determinant that goes with the 0 is. So I eliminate its column also, and you can see we're left with -1, 2, -4, 1. Now for the 2. We had to go plus, minus, plus. So I've eliminated his row, I eliminate his column, I'm left with 3, 4, and 2, 1. And lastly, for this 1, I've eliminated his row, I eliminate his column, and you can see we're left with 3, -1, and 4, -4. Hope y'all were able to see that, eliminating rows and columns. Now we just do the little 2x2 determinants and we're finished. I don't even have to do this arithmetic right here. That's 0 times some number. That's finished. That's why we picked that row. So let's go right here. -2 times 3 minus 8 plus 1 times -12 minus -4. Just multiplying those 2 by 2's. 3 times 1 minus 2 times 4. 3 times -4 minus -1 times 4. So -2 times -5 plus 1 times, we're getting -12 and 4 is -8. So 10 minus 8 is 2. Same determinant we got when we worked this exact same matrix earlier. Whether we did it by diagonal method or whether we did it by expansion by minors, you'll always get the same thing. Let me put one more up here for you to try on your own. And do this by doing expansion by minors with the second row. 0 is in the second row, so that's the one I want to use. So let's do expansion by minors using the second row. You take a couple minutes to work this, and I'll wait right here. So hopefully you got the solution. We should know that it's 5. It's the same one that we worked a minute ago, but let's go through and check and make sure you did it correctly. First off, we want to work off row 2 because that's where the 0 is. If I didn't have a 0, I could pick any one of them. Probably would have picked row 1 because here I'm multiplying by 1. Just simplifying your calculations. But we're going to work off row 2. So we're going to write out 0, 2, and 3. Now, let's put the signs on there. Remember, row 2 is minus plus minus. So it's -0, +2, -3. And we set up each of our individual determinants, our little mini determinants. So we've eliminated row 2, because that's what we're expanding off of. Now we want to find the matrix for 0. It doesn't really matter because it's only going to all cancel out anyways, but just good practice to get. So eliminate his row, eliminate his column, and you can see we're left with 1, 2, and 4, 2. 1, 2, and 4, 2. Now the 2. We've eliminated his row, eliminate his column, and you're left with -1, 3, and 2, 2. Nope. -1, 3, and 2, 2. And finally, the -3, or the 3. We eliminate his row and his column, and you're left with -1, 1, and 3, 4. Go through and do the calculations now. 0 times all that becomes irrelevant at that point. 0 times a scalar, right? Multiply all those. But we're just going to, sorry, matrix times a scalar. But 0 times whatever that number comes out to be will be 0. 2 times -2 minus 6, right? -2 minus a positive 6. -3 times -4 minus a positive 3, so -3. 2 times -8 minus 3 times -7. -16 plus 21 equals the 5 we got earlier from the diagonal method. So whether you want to use expansion by minors or diagonal method for a 3 by 3, it's your personal preference. There are times when the expansion by minors is faster. You can see it's smaller, calculations are broken up. Still need to know expansion by minors because you are going to see this again when you get up into calculus. Probably not Cal 1, but I'm pretty sure it's Cal 2 where you see it and use it quite a bit. So, expansion by minors, diagonal method, that's how we find the inverse or the determinant of a 3 by 3 matrix. And then just left diagonal minus the right diagonal gives us the determinant of a 2 by 2 matrix. Next we'll talk about inverse of matrices, but I'll see you in class tomorrow if I don't see you in that lecture before then.